Let's do an experiment. Add some food color to cold water and hot water. What will you observe? You can see the color mixes quickly and homogeneously in hot water rather than cold water. Why is it so? This is because at higher temperatures, water molecules move faster and dissolution occurs at a faster rate than at low temperature. This means the rate of reaction is temperature dependent. It is observed that reaction rate increases with increase in temperature. In fact, an increase of 10 degrees Celsius in temperature doubles the reaction rate. In this video, we'll see the equation relating temperature and reaction rate. The Arrhenius equation gives a relation between rate constant and absolute temperature. The rate constant K equals A into e raised to minus EA by RT. Here, R is the universal gas constant, EA is the activation energy, and A is the Arrhenius factor or frequency factor. Note, the frequency factor A is a constant for a particular reaction. For better understanding, you may consider the reaction between hydrogen and iodine. According to Arrhenius, this reaction can take place only when a molecule of hydrogen collides with a molecule of iodine. Upon collision, an unstable intermediate will be formed. This intermediate is called activated complex. This exists for a very short time. The breaking of this intermediate results in the formation of two molecules of hydrogen iodide. The energy required to form the activated complex is called activation energy. You can realize the activation energy by plotting potential energy against reaction coordinate. In fact, the peak of this curve gives the activated complex. Thus, activation energy is the minimum energy required to cause a reaction. And when the activated complex decomposes to form products, the energy is released. However, the final enthalpy of the reaction depends on the nature of reactants and products. Next, we will discuss more about the exponential term e raised to minus EA by RT in the Arrhenius equation. To understand this, you may recall the collision theory. According to collision theory, only a small fraction of collisions is effective and result in the formation of products. Effective collisions occur only if the reactant molecules possess a minimum kinetic energy called threshold energy, and these molecules collide with proper orientation. It is doubtless that all the reacting molecules do not have the same kinetic energy. In order to predict the behavior of a large number of molecules, a statistics is required. Maxwell and Boltzmann described the distribution of kinetic energy of molecules by plotting the fraction of molecules with a given kinetic energy against the kinetic energy. This gives Maxwell-Boltzmann distribution curve. The peak of this curve gives the kinetic energy of maximum fraction of molecules and is known as the most probable kinetic energy. Note, here only those fraction of molecules to the right of the activation energy take part in the reaction. Now let us see what happens when the temperature increases. When the temperature is raised, the maximum of the curve moves to the high energy value. Also, the curve broadens out. So when the temperature is increased, there is a greater proportion of molecules with much higher energy. Thus, increasing temperature increases the fraction of molecules which collides with energies greater than activation energy EA. This indicates that rate of the reaction increases with temperature. Therefore, in the equation, the factor e raised to minus EA by RT gives a fraction of molecules with energies greater than EA. Taking the natural logarithm on both sides of equation, you will get ln K equals minus EA by RT plus ln A. This equation can be considered in the form of y equals mx plus c. Hence, a plot between ln K and 1 by t gives a straight line with slope equals minus EA by R and y-intercept as ln A. This graph helps you to determine the activation energy of a reaction. Besides, this graph clearly shows that as temperature increases, the rate constant increases exponentially. Consequently, activation energy decreases. The natural logarithm can be converted to log to the base 10. Then the equation may be written as 2.303 into log K equals minus EA by RT plus 2.303 into log A. Next, we will see the relation between rate constant at different temperatures. If K1 and K2 are the values of rate constants at temperatures T1 and T2 respectively, then you may write separate equations as at T1 ln K1 equals minus EA by RT1 plus ln A. Let this be equation 1. At T2, ln K2 equals minus EA by RT2 plus ln A. Let this be equation 2. Now subtract equation 2 from equation 1. Rearranging and taking log to base 10, you will get the equation as log K2 by K1 equals EA by 2.303 R into T2 minus T1 divided by T1 T2. Thus, Arrhenius equation can be used to calculate the activation energy at different temperatures if the experimental value of rate constants are known. Now, try to find the answer for the following observation. For enzymatic reactions at low temperatures, an increase in temperature increases the rate of an enzyme catalyzed reaction. However, at higher temperature, the rate of the reaction dramatically decreases. Why? Try to find out this. Now, we will summarize what we have learned today.
Manorama Horizon. Learning made simple.